We now want to sketch the output response due to the input applied at time n equals 0 to this system. Our input was a value of 2, and what you can see then that let's say here's 1, 2, 3, and 4. This is now y, the component of the output due to the input at time 0. This is now that component, y sub 0 of n. We had the pulse response had a value of 1/2 at time n equals 0. We want to scale that by 2 because our input that we are applying is of magnitude 2, which means then that we're going to have this value of, if I could do my multiplication properly, we are going to have a value of 2 times 1/2, where we will produce an output of 1, and that value is just found by taking the input at time 0, which is notation-wise x of 0, scaling the pulse response at time 0 by that input value, and that's now 2 times 1/2, or a value actually of 1, and that's this y sub 0 of 0 component of the 0th output at time n equals 0. At time 1, we now had a pulse response at time 1 equal to 3/2. We scale that by 2, and we will then have a value of 3 for that particular piece of our output response. That's going to be x of 0 times h of 1, which is equal to 2 times 3/2, or 3, and that's now y sub 0 of 1. Meaning if we applied an input at time n equals 0 of value 2, we are just going to double the original pulse response that we started with for this particular system. At time 2, we now have a scaling of the pulse response at time 2, and that typically for, well, in this example it was 2, which we hit with another 2, which is coming from x of 0. This particular value is then x of 0, h of 2, which is 4, and that's now y sub 0 of 2. We have one more time instance because this guy continues to evolve 3 units after we apply the input. In this case, it went down to a value of 1 for our pulse response. We scale that by 2 because of x sub 0 being 2, and this now gives us 2, which is y sub 0 at time 3. That's the first component of our total output response. This is the component due to the input applied at time n equals 0. Let's now look at the next component of our output, which is the output response due to the input x at time n equal 1, and that particular value for our input was -1. Consistent with what we had done with notation before, let's now call that output response, or that component of the output, let's call that y sub 1 of n. Again, where this 1 is due to the value of the input at time n equal 1, where now this y sub 1 of n is the component of the output due to the input applied to the system at time n equal 1. We know what the pulse response looks like when we had a pulse of 1, or that's by definition what the pulse response is. Now we have an input, a plot of amplitude -1. But this particular input doesn't begin until n equal 1, and the system naturally does not react to that particular input until the input is applied. That's because the pulse response does not begin before n equals 0. In this case, if you look at what we have, we now are saying here is our response due to the input applied at n equal 1. Here is our index of time n, 1, 2, 3, 4, 5. Because of this particular system that we are dealing with, its pulse response begins to respond to an input applied exactly when the input is applied. No delay involved. Meaning, if we now apply an input, which we are doing now, or that's what we're investigating, we're now investigating that particular input, that's occurring at time n equal 1. If that didn't have a value of -1, but if it had a value of 1, we would simply have a output response due to that component of the input beginning with a magnitude of 1/2, then 3/2, then 2, and then 1 at times n equal 1, n equal 2, n equal 3, and n equal 4 respectively. But since this is actually an amplitude of -1 for our input, all we really have to do is invert those numbers to obtain this component of the output, which is y sub 1 of n. Meaning, we now have the ability to sketch the response due to this input applied at time n equal 1. It's going to be just the inverse, or the negation, I should say, of the original pulse response at beginning at the time when we apply the input. We apply the input at time 1. That says then that we will have a response of -1 times the pulse response at time n equals 0, which is 1/2 times -1, or -1/2. This value is then x at time 1 times h of 0, which is -1 times 1/2, or -1/2, and that's going to be y sub 1 at time n equal 1. Because this particular component of the response, y sub 1 of n, is not going to have any non-zero value prior to the application of that input component occurring, which is occurring at time n equal 1. Meaning the value of y sub 1 of 0 is 0. What about the next value? Well, that's just a scaled version of the pulse response at one time unit of distance or time after the application of the input. In this case, that's now h of 1. So this is now x of 1, h of 1, and x of 1 is -1, h of 1 is 3/2, so this now becomes -3/2, and that's y sub 1 at time 2. And if we now sketch that, that's now down here at minus 3/2. We then scale the pulse response 2 units of time beyond the application of the input. The input was x of 1. 2 units later is h of 2. That's now minus 1 times h of 2, which is 2, or this is now minus 2, and that's actually y sub 1 at time n equal 3. Finally, we now have x of 1, the input that we applied at time n equal 1. The response is going to linger for 3 units of time thereafter because that's the length of our pulse response, or we now scale h of 3 by the input at time n equal 1, which is minus 1. The pulse response at time 3 is 1, and we have then minus 1, and that's y sub 1 of 4. That now produces the response of our system due to the component of the output response due to the input at time n equal 1. We only have one non-zero term left in our input applied to the system of the 3 that we applied, and this is now going to be the output response of our system due to the input applied at time 2, which was actually 1. And I do not think it's going to come as any surprise that we are going to call that component of the output y sub 2 of n. And that's the output component that results when we apply an input at time n equal 2 to the system. In this case, we now have 1, 2, 3, 4, 5. This is going to be y sub 2 of n. We are not applying, or this component will not start producing a non-zero value until the application of the input. The input is not applied until n equal 2, which means that up to that point we are not going to see an output, meaning y sub 2 of 0 is 0, y sub 2 of 1 is 0. The first non-zero response is going to be occurring exactly when the input is applied in terms of time, and that time was at n equal 2. At n equal 2, we are going to obtain then our y sub 2 at time 2, which is going to be x of 2 scaling the pulse response the instant the input is applied, which is h sub 0. H sub 0 again was 1/2. This particular input value or scaling is 1, and so now all we have to do is sketch the original pulse response delayed in time 2 from the actual start of this system response, because this is now our input applied at time 2 component that we're looking at. This is now going to be 1/2, 3/2, 2, and 1 at time 2, 3, 4, and 5 respectively. What we're doing then is we see that y sub 2 of 2 is x of 2, h of 0, which is 1 times 1/2, or 1/2. Y sub 2 at time 3 is the same input. Now it's what the system does 1 unit of time later after the application of the input, which was to say that in this particular example it now moves up to 3/2 scaled by the input's value, y sub 2 at time 4 is still responding to the input applied at time n equal 2. It's now x of 2 h of 2, which is 2, and finally the last non-zero piece of this component of our input is y sub 2 of 5, which is x of 2 h of 3, which is 1 times 1, or 1. To find or to actually determine the total output response, we need to simply add up all of these three components at the appropriate points in time. We've now looked at this in pieces. We created the first piece due to an input at time n equals 0. The second component was due to the input applied at n equal 1. And the third component was the response of our system due to the input at time n equal 2. We now want to find or compute the total output response. We now have the individual pieces already determined, and there's 3 of those. What we are wanting to do now is find the total output, which we will not put a subscript on. We'll say that's y of n, but that's going to be based or created by combining the component due to the input at 0, the component due to the input applied at n equal 1, and the component of the output due to the input applied at n equal 2. If I can squeeze this commentary in, these components there's the component due to the input at n equals 0. This is the component due to the input applied at n equal 1. And this is the component due to the input applied at n equal 2. Let's now calculate the y of n for the different values of n itself. In particular, at n equals 0, what we now need to do is add up all of the pieces that combine. We have y sub 0 of 0, we have y sub 1 of 0, and we have y sub 2 at 0. But if we go back and look at what that is, we'll actually see that there's only one non-zero piece associated with the total response at time n equals 0, and that is x of 0, h of 0, which comes from the first component, y sub 0 of 0, and that's equal to 1. Let's now look at the total response when n is equal to 1. That's going to be y at time 1, which is the first component, y sub 0 at time 1. It's the second component, y sub 1 at time 1. And it's the third component, y sub 2. at time 1. If we add those up, this now is y sub 1. That's now h of 1, x of 0, plus h of 0, x of 1, and those are the only two non-zero values. H of 1, x of 0 was 3, h of 0, x of 1 was minus 1/2, and so we now have 2.5 or 5/2 for the total response at time y of 1, at time n equal 1, which is y of 1. Let's now look at the next time index, n equal 2. This is now going to be excuse me, y at time 2, which is the first piece, second piece, and the third piece, all at n equal 2. The first piece is really the response due to an input at time applied at time 0, where the pulse is now 2 units delayed, or this is now h of 2 x of 0. The component y sub 1 at time 2 is 1 time step beyond the application of its input, which was x of 1, and y sub 2 of 2 is actually the pulse response at time 0 scaled by the input applied at time 2. Numerically, this is 4 minus 3/2 plus 1/2, or 4 minus 1, which is 3, and that's the value of our output response at time n equal 2, the total response. Let's now look at the total response at n equal 3. At n equal 3, we do exactly the same thing that we've just been doing. We have the 3 pieces. We have a piece due to the input applied at time 0. We have a piece due to the input applied at time 1. And we now have a piece due to the input applied at time 2. And we're looking at all 3 of those components' contribution at time n equal 3. Y sub 0 of 3 is now already corresponding to 3 units beyond the application of its input at time n equals 0. So this is now h of 3 x of 0. Y sub 1 of 3 is now 2 units of time beyond the application of the input at time 1, and y sub 2 is now 1 unit of time beyond the application of the input at time 2. This now is going to be 2 minus 2 plus 3/2, or now we are left with 3/2 for the total response at time n equal 3. Now, what's happening at time n equal 4? This is now the total response at time 4. We would be wanting to add in the component due to the input applied at time 0, the component of the output due to the input applied at time 1, plus the input of the component of the output due to the input applied at time 2. Remember, though, this particular system had a pulse response that only continued 3 units of time beyond the application of the input. Meaning, if we apply an input at time 0, it's going to now have decayed down to 0 after 3 time units beyond that application of the input. And so, consequently, we do not have a value associated with the input applied at time 0 at time n equal 4. We do have, though, the response due to the input applied at time 1, 3 units later, which gives us y sub 1 at time 4, will be h sub 3 x of 1, and y sub 2 of 4 is now 2 units beyond the application of the input at time 2. This is now minus 1 plus 2, or 1, for the total response of our system at time n equal 4. You can see that we're starting to die out in terms of components that are producing an output response, we now are wanting to find what is the last piece of this output response. In general, we have y sub 0 of 5 plus y sub 1 of 5 plus y sub 2 of 5. But at time n equal 5, we're 5 beyond n equals 0, we're 4 beyond n equal 1, and so those two components have already contributed all they're going to apply. We're simply left with the response component due to the input applied at n equal 2, which is 3 units later, so that's h of 3 x sub 2, which is 1, and that's now the output response at time y equal 5. If we put all of those pieces together, that will now be our total response of this system. Here is n, and here's y of n, and I'm probably going to forget some of those values. But we started with n equals 0, and we only had the response due to the input at time n equals 0. At time 1, we had the contribution due to the input at 0 and the input at 1, giving us 5 halves. At n equal 2, we now had all three components contributing. At n equal 3, we still had all the inputs contributing, but now by n equal 4, the component of our the input at time n equals 0 is not producing an output 4 units beyond the time application of its input, and consequently we are going to then be finished with our response, and this is now the complete response. We had a pulse response of duration 3, we had an input of duration 2. It's no coincidence then that the total response has a duration 5, which is 2 plus 3. You can now see that if you look at all of these pieces that we've built up, here is the piece due to y of 0. Here's the piece due to y of 1. Here's the piece due to y of 2. And I hope you can see the pattern. Here's x0, h0, 0. Here's h1, x0 plus h0, x1. h2, x0, h1, x1, h0, x2. Same pattern. h3, x0,